So, setting up number 1. So the car drives over a bump in the road, draw force diagrams. Right. So definitely we would have mg down, normal force up, yes? What is B asking us to find? Can you read it to me, please, Brett?
Find the speed in kilometers an hour at which the driver will experience apparent weightlessness.
What's apparent weightlessness? That's a condition. And that condition, when you are apparently weightless, when do you feel apparently weightless? Yes. When the normal force is 0. So look at that free body diagram that I wrote. First of all, who's winning? What path are we tracing out? I've never used the word arc. A circle, so I know it's going to be winner minus loser equals Fc equals circular force. So, and if I want the normal force to be 0, what we're really saying is when is gravity? And then you need to ask yourself, which equation do they want you to use for Fc, mv squared over r, or m4 pi squared r over t squared? Because and solve for v. Oh, you'll notice the masses cancel conveniently. Oh, does everybody in the car feel weightless no matter how much they weigh? Yeah. That's what we're talking about there. Okay? Oh, and if v was faster than that, you'll actually have, strangely enough, a negative or some kind of bizarre, you'll leave the ground. The normal force will be enough that you'll leave the ground. It'll push you up. But we're not, that's a complicated, forget it. Any others before number 9? 5. Sorry? 5? 5? Okay. Can I do 5 right up here where I have number 3? In terms of, we're spinning it in a vertical circle. Do you remember we did say we know when the rope is most likely to break at the bottom. So I'm going to assume that we are right there. I have tension up, gravity down, but I know tension is winning because my net force has to be towards the middle. Oh, Mr. Dulac, I said, I just said I know tension's winning. My equation is going to look like this. Tension minus mg equals, and they're asking about speed, so it's going to be mv squared over r. Yes? Is that next door? Give me 1 second. So I think we can, tension they gave me, yes, Brett? Yeah. Mg I know m, I know r. I can solve for v. It's going to be a little tricky to get the v by itself, but eventually I'll be able to. I would probably crunch this first and just get a number here. Whatever 30 minus that times 9.8 is, get that number there, and then times by r, divide by m, and then square root. That should get you there. Did you try that?
I had that set up just like with all the variables, just didn't want to work out for it.
Okay. Yeah, you know what? I wouldn't try and get the v by itself. I mean, sorry, that's a fib. For you guys, I wouldn't recommend getting the v by itself because it involves fractions and yuckiness. If you want to get the v by itself, for what it's worth, you would times by r, times by r, times by r, it would cancel, and then divide by the mass. You would get v equals tr minus mgr divided by the mass square rooted. But that's a complicated enough expression that I would...
I wrote plus mgr.
Oh, there you go. That was easy. You got that far? You got that? I'm impressed. Maybe you guys don't suck at fractions. Number 9. I think I like number 9. I think I like number 9. I think I like number 9. Number 9 is a nice question. Also, this is a nice picture. Let's label our forces. Vlad, gravity down, yes? And normal force up, same magnitude, I'm pretty sure. Now, he's moving in a circle, so there has to be a net force pushing it towards the center. Which force? No, we never put Fc on a free body diagram. It's never going to show up on a free body diagram. I curse you when I say, no, it doesn't show up on my free body diagram. It's going to show up in my equation on the right-hand side. It's going to be that. What force is pushing him in a circle? What? How do you know that? Why can't you do corners on ice very well? Less friction. Friction. Here's your equation. Friction is mu times the normal force. Oh, I don't know the normal force. But look, 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 look. I know the force the same size as the normal force. What? And it's going to be mv squared over r. I see they gave me a speed. Vlad, please notice they gave it to you in kilometers per hour. That's yucky, so you have to divide by 3.6. And then you should be good to... Oh, turns out they didn't give me the mass of the car for a reason. And I can solve from you. Take the rest by yourself? Yep. The banked curve, for what it's worth. As you're getting your licenses, as you're driving, you may notice that many corners are not level. They bank them, especially freeway on-ramps and off-ramps. Why? It's good physics. What are the forces acting on this car? Get the obvious ones. We have gravity down. We have normal force. Which way is my net force? Toward the center. If I add these two together, tip to tail, if I add gravity and normal force, I know to stop exactly right there, not draw longer, not draw shorter, because I know I need my net force pointing towards the center. Oh, I don't know the normal force. Mr. Dewick, let's think about your free body diagram, because you got the normal force as the hypotenuse in your triangle, but you've got mg in the hypotenuse on the bottom triangle, and you want to argue that normal force is equal to mg perpendicular as opposed to mg parallel. Give me a second and let me think about this here. Oh, you know what? We're keeping normal force in our equation. I'm going to get rid of that. I'm looking at what they have here. So in terms of force equations, we end up with that's theta, remember from our good old force diagrams that we did a bunch of, and I think that means that, I think this is angle theta right there if I really draw a few extra lines and jump around, but it looks like it if I've been roughly to scale that that's the smaller angle anyhow. It says write the force equations, so do you get, let's see, adjacent hypotenuse, if you want to relate gravity to the normal force, is it cosine? Yep. If you want the normal, relate the normal force to circular motion, is it sine? Oh, that's an O, Mr. Dewick. Yep. Okay. I'm not going to ask you to find the banking. I'm not going to give you a banked curve, but what do you notice, which force didn't appear here that we had to include when we were looking at Vlad's circular motion question one question ago? Friction. The reason we bank corners is, as it turns out, even if the corner is completely ice covered, if you hit it at the speed that it says, friction is irrelevant. You'll be fine. In fact, if you go too slow, you could actually start to slide down the corner, slide down the banked curve, because you haven't hit the right speed and there is no friction to keep you in place. Or if you go too fast, you could actually slide up and off the corner. Banked curves, turns out, are irrelevant of weather. Look at the speed limit, hit it at that speed limit. It's kind of nice. So 11 says, it is important to bank a corner whenever a vehicle is moving at high speed. Why is a flat corner? Flat corner, the force that's turning you is friction, and friction can only be so big, and friction is weather dependent. Why can a banked corner be safe? No friction required. Now it says, be safe at high speeds. You have to hit it at the right speed. Do they, on banked corners, always post a speed limit? Really? No. Someone thought of that? Yeah. Now you know. Any other questions from the homework? So today's lesson is going to be partly review, but we're going to be going into a bit more in-depth. We're going to be looking at universal gravitation. But first, I have for you a take-home quiz. Lesson 4, universal gravitation. We're going to go cosmic, and when we go cosmic, we're not going to be able to say, hey, what's FG, MG? Because the further you get from Earth, that 9.8 changes. So we're going to look at what we call universal gravitation. This is what we refer to as the law of gravity. This is one of the many things that Sir Isaac Newton came up with. We have said that gravity is a force, read along with me, that exists between the Earth and masses on its surface. In fact, gravity is universal. It exists between any two masses in the universe. One of the qualities, one of the characteristics that mass possesses is anything that has mass sends out a gravitational field that exerts a force on anything else that has mass. All of you right now are sending out a gravitational field. A very, very, very small, Courtney, gravitational field. Gravity, there are 4 fundamental forces. Gravity is by far the weakest of them. Yep.
It's like the smallest you have to be to like be in space, and that's something like.
Because you're in outer space, anything can orbit around you because there's no other forces. And you would, even if you were exerting a very, very small force, you'll be fine. We're looking at orbits next class, so I'll come back to that. Yeah?
It's another orbit question.
Yep.
Would Shaq have a bigger orbit than us by a lot?
We can crunch the numbers in just a second. Okay. Gravity is universal. This is what you want to realize. It exists between any two masses in the universe. So here's two masses, big M and little m. We'll traditionally in Physics 12 use big M to be the planet, the bigger body, and little m to be the satellite, the moon. You know what? Let's big M, Earth. Little m, moon. Does the Earth have mass? So it will exert a gravitational force on the moon. Does the moon have mass? It will exert a gravitational force on the Earth. Here's what we're going to ask ourselves. Compare the forces, the gravity forces on the two masses. A, the force exerted by M is greater. B, the force exerted by little m, the moon, is greater. Or C, they're the same. Once again, we're going to vote. Once again, how high you hold your hand up is how sure you are of the answer. I'm positive, pretty sure, gut instinct. Duke's going to make fun of me if I don't vote. Okay? Who says A? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. Who says B, the moon exerts a bigger force? Who says, forces are the same? 1, 2, 3, 4. Who didn't vote? So as usual, you can attack or defend. You can attack someone else's answer saying it has to be wrong, or you can defend your own answer as being right. Convince me.
Just feel like the hardest one to comprehend always seems to be right.
So you picked C because it seems like the weirdest? C is right.
Oh, nice. Nice strategy one.
Why? You may remember when we started looking at forces way back when, almost certainly I brought out a bathroom scale and I had two people push against the bathroom scale to exert a force between each other. Probably two smaller girls is usually what I pick. And then I say something like, who thinks they can do better? And there's always some big husky football player or person, I can push harder than that. But I kept one of the girls up there and I brought in my big husky football player and I had them push and they couldn't do better. And the reason they couldn't do better was because the smaller person couldn't match their force. And we used that to illustrate Newton's third law. What was Newton's third law? Louder, what? If the Earth exerts a force on the moon has to exert a force on the Earth, and they have to be the same size. Now, the magnitude of the force is the same. The effects are not. So instead of going Earth and Moon, let's go Earth and coal. Okay? The Earth is pulling down on coal right now. Coal is pulling back up on the Earth with exactly the same magnitude, except our basic definition of force is what times what? The basic definition of force is what times what? Mass times acceleration. Who has a bigger mass, the Earth or coal? Huge mass. How much acceleration will the Earth actually experience? Zero. Zero. Oh, and also, you know what? The odds are, with our 7 billion person population, that somewhere exactly on the other side of the Earth, there's probably somebody about the same mass as you, roughly, exerting a force in the opposite direction and canceling them out anyways. It's why, even though all of you are exerting forces on each other, you know what? There's a lot of canceling out forces, because you're roughly surrounded by people in all directions of equal mass. Roughly. But you do exert a force on the Earth of the same magnitude. You have a much smaller mass, so your acceleration is, I know exactly, 9.8. Earth's basically zero. Gravity's small. So small that it was very, very difficult to measure a key fundamental constant. Cavendish and a few others came up with some very ingenious experiments, and I'll show you a couple of videos of what they did a bit later on. But here is the universal gravitation equation. Fg, force of gravity, equals, leave a small space, room for one letter. They said it depends on the product of the two masses in question. If you multiply the two masses together, that helps you calculate the force, divided by the distance between them squared. Now, that'll get you the force, but that won't get you the force in newtons. You need a conversion factor to get an answer in newtons. Just like if we want to go, for example, from kilometers per hour to meters per second, our conversion factor was divided by 3.6. That was our conversion factor. The conversion factor is, we symbolize that with a capital letter G. And it has a magnitude of, right here, 6.67 times 10 to the negative 11. It has a magnitude of 0.000000000667. Sebastian, really small. It took them a long time to actually manage to measure that, to find it directly. So, what does that mean? Well, we'll chat for a bit. Okay? So, let's quantify this. Let's suppose let's pick some nice numbers. If we have two 1 kilogram masses separated by exactly 1 meter, how much gravitational force of attraction is there between them? Can you feel them tugging towards each other? Let's find out. We would say, first of all, our gravitational force equation is big G m1 m2 over d squared. And we said that big G is your conversion factor. It's Newton's universal gravitational constant. It's on your formula sheet, but most of you will get tired of looking it up. You'll end up just memorizing it. It's 6.67 times 10 to the negative 11. A few of your calculators might have that actually built in. If you see somewhere on your calculator a capital G, because some calculators do have constants built in, you can use it. Don't go hunting for it right now. Mass 1 is 1. Mass 2 is 1 divided by 1 squared. Don't you dare reach for your calculator to crunch the numbers here, because this is your 1 times table times your 1 times table divided by your 1 times table times... You know what? You get... Is that a very big force? No. You wouldn't feel it. In fact, we would need very, 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 very good instruments to even detect that. Gravity is weak. Now, if you have a huge mass, like the Earth, you think it's strong because it's the force that dominates your life. But you need such a huge mass, and it's not that strong. We can defy gravity by flying airplanes, by launching rockets. We can defy it fairly easily. So, example 3. Let's rewrite the equation. The equation, it was Fg equals big G m1 m2 over r squared, or d squared. By the way, we're going to replace the d with an r eventually when we start looking at orbits, because orbits are circular, and why not call it a radius? We'll flip-flop between d and r. What have we said now? I walked you through this with my two stooges here in the front. If we double the distance, what happens to the magnitude of the force between them? Sorry? 4 times smaller. So I think we can say it's going to be the force divided by 4. Instead of saying 4 times smaller, 1/4 as small. Yes? What if we triple the distance? Or are you German saying no? No, 9? Yeah? Okay. Quadruple the distance? By the way, what this also means is if you're talking about space travel, the further you get away from the Earth, the easier it gets. But it's that initial, this is why they build 3-stage rockets. That first stage is just to get you part of the way, and then you need to ditch that extra mass, and because you've used that huge engine, you burned up all the fuel, now it's just dead weight, ditch it. The second stage gets you up closer to orbit, but once you get there, ditch it, you don't need it anymore. Third stage, you don't need a big rocket to get the rest of the way to the moon. What if we double one of the masses? So what if we double one of the masses? That would put a 2 right there. How will that, I think it'll make everything just twice as big, yes? 2F. What if we double both masses? Yep. What if we cut the distance in half? Now, you're cutting it, you're getting closer, so the force is going to be stronger. There's a 2, but the 2 is squared. It's going to be stronger by a factor of what? Yeah, it's going to be 4 times stronger. So not F over 4, 4 times stronger. Yes? What if we cut the distance in 3? It'd be 9 times stronger. What if we, don't write this down. What if this became a 0? Calculus students, what's the limit as d approaches 0 of that equation? This is what Stephen Hawking asked in the 70s. And he said, well, it appears to me that the smaller that number, the bigger the force. The smaller that number, the bigger the force. Yes? If that was a really, really small number. If you had a whole bunch of mass contained in a really, really small area, you'd have a huge gravitational force. What are we talking about here? There's where he said, I think this is the math of a black hole. We joke a black hole is where God divides by 0, right? Or where the universe divides by 0. What if we double both of the masses and we double the distance? Doubling both of the masses would give you 4 times bigger. Doubling the distance will give you 4 times smaller. Oh, I think they just cancel out. I think you just have your original force, F. Right? Sean, gravity is usually minuscule unless one of the masses is huge. For instance, a planet or a star or a moon. Turn the page. Assume the mass of the Earth is 5.98 times 10 to the 24th kilograms, which it is roughly. How do we get that, patients? Its radius is 6.38 times 10 to the 6. Both of these numbers you're going to be using lots. Both of these are on your formula sheet. This is going to be the unit where you're going to be using the data section of your formula sheet an awful lot. Although some of you will memorize some of these. I generally have these memorized while I'm doing the unit, but by the end of the year I've forgotten them, so they are on your formula sheet. Find the force the Earth exists on a 50-kilogram person right on its surface. And because the radius of the Earth is so big and the person's height is so small, we can ignore the person's height when we're talking about the overall distance from the center of the Earth. So, okay. Big G, big M, little m, all over. And now I'll use r squared because it's a radius. You get 6.67 times 10 to the negative 11. 5.98 times 10 to the 24th. What was the mass of the person? 50. Divided by 6.38 times 10 to the 6th squared. I strongly encourage every one of you to try this on your calculator. This is going to be about as big as and complicated as we get in terms of scientific notation and multiple terms. This is your chance to learn how to type this in. And I think you're going to get something like 489.99 or something, 490. That's what your goal is. Now, this shouldn't surprise you because we could have just gone, hey, FG is mg. But the fact that we could get the 490 by going mg. Now, let me pause for a second. Who can't get the 490? I can come help you with your calculators. There's a few of you. So what I wrote here is, this shouldn't be surprising because if we calculate FG equals mg, we get the 490, but the fact that I get the same answer using the more complicated universal equation at least suggests to me that that universal equation is correct. Oh, and Sean, it suggests to me that if I move out to outer space, if instead of the mass being right here, if it's right here, as long as I know that distance, I can use the more complicated universal one, and I can find the force of gravity out there on this object. Not only that, this is going to give us a different way to calculate the gravitational field. Now, up until now, we've had two ways to calculate the gravitational field. Now, the gravitational field strength of the Earth is units. Graydon? Or it's also newtons per kilogram because if it's an acceleration, doesn't that automatically mean it's a force divided by a mass? Okay. There up until now have been two ways to calculate that 9.8. The first is to hang a mass from a scale. If you know the force in newtons on the scale, and you know the mass in kilograms, and you divide, you'll get 9.8. We haven't done that one. What we've done in Physics 11, we used the free fall method. The second method was to drop an object and measure its time in free fall. We can get 9.8. I think all of you tried that last year in Physics 11. Some of you got close to the 9.8. We were a little reaction time, but we could see, yeah, good equipment, it could be done. Okay? If we compare these two methods, it's going to give us a third way to calculate the gravitational field. Specifically, how did they figure out the gravitational field of the moon before they went there? It's not like they could go there and hang a mass from a scale, divide the number of newtons by the mass, and find its acceleration. It's not like they could go there and drop something. They had to know ahead of time. Or, how do we know the gravitational field strength on Mars? We haven't been there yet. How do we know the gravitational field strength of Jupiter? We haven't been there yet. We can go like this. Gravity equals gravity. We can go like this. Gravity equals gravity. On the Earth, we've written gravity as universally, gravity is right? This gives us, and this G is the gravitational field strength. Yes, it's also the acceleration due to gravity in free fall, but the reason that's the acceleration due to gravity in a vacuum and free fall is that's the gravitational field strength. And here's how you can calculate it. It looks like you can calculate it by going big G, big M over R squared. Where big G is 6.67 times 10 to the negative 11. That's the universal constant due to gravity. Big M is the mass of whatever planet you're dealing with, which can be calculated. We'll talk about how you do that. R is the radius of whatever planet you're dealing with, which can be figured out from telescopes and things and observations. And, you can figure out what the gravitational field of that planet is before you get there. So, gravitational field strength is big G, big M over R squared. This formula is not on your formula sheet, but you will need to know it. Did I just show you how it's actually hidden inside the force of gravity equation with the derivation? That's how you can find it. Okay. So this is gravitational field strength. What that lets you do, suppose you want to put a satellite out there somewhere. This would let you calculate what the gravitational field strength is going to be out at that distance. So if you have some kind of a point, a field point we call it, out somewhere, and you want to know, hey, what's the gravitational field strength? Not what the force of gravity is, because there's no force until I put another mass there. But what the acceleration due to gravity is, what the gravitational field strength is, I can crunch the numbers and find out. This last property is useful because it provides us with a means to calculate the mass of the Earth. I said to you, hey, how did they figure out how heavy the Earth is? It's not like you can throw it on a scale. We did this. The radius of the Earth has been known for about 2,000 years. You can measure it using the geometry of the sun's rays. A Greek mathematician named Eratosthenes came very, very close. He got the radius of the Earth to be about 6.5 times 10 to the 6th. Since then, we've done better. But we know the radius of the Earth. You can also calculate it by looking at the curve of the horizon as a ship vanishes over the horizon. There's all sorts of ways to crunch the radius of the Earth. It was getting the mass of the Earth that was tricky. How the heck can we find that? I know the value of G on the Earth, it's 9.8, but I also know a means of calculating it. It is big G, big M over R squared. That's the gravitational field strength. Do I know this? 6.67 times 10 to the negative 11. Have we known the radius of the Earth for about 2,000 years? Yep. Is it fairly easy to calculate that 9.8 by dropping something and timing it? Yep. And suddenly, once Cavendish had found this number, one of the first things he said was, "Ah! Now I can find mass of the Earth." Up until then, it had been speculation. Let's get the mass of the Earth by itself. Mass of the Earth looks like it's going to be 9.8 times the radius of the Earth squared divided by big G. Is that right, I think? Mass of the Earth is going to be 9.8 times 6.38 times 10 to the 6th squared, all divided by 6.67 times 10 to the negative 11. I already told you earlier that the mass of the Earth was, we used it here, 5.98 times 10 to the 24th. See if you get 5.98 times 10 to the 24th.
Would that G be the same on Mars?
That's universal. Not only would it be the same in Mars, it would be the same in the galaxy Andromeda. If you're measuring in kilograms, and meters, then G will, and you want an answer in newtons, then it's going to be 6.67 times 10 to the negative 11. It's Newton's gravitational universal constant. As far as we know, it's the same anywhere in the universe. Do you get 5.98 times 10 to the 24th? This was a happy day when Cavendish was able to calculate this. I'm the first guy to know what the Earth weighs. Woohoo! They'd done rough estimates and calculations, because you can also do a rough estimate by looking at the volume of the Earth, which you can figure out by if you know the radius, and guessing as to the overall density of the Earth, and you can get some good rough. But the overall density of the Earth is not constant. We have that iron core at the center, which is much, much denser. And by the way, the fact that the value they'd been using was too low was one of the things that led them to speculate that there must be something denser in the middle of the Earth that we haven't detected that's denser than normal rock. You get 5.98. Come on, pen. 5.98 times 10 yoink to the 24th kilograms. But I need to make this a subscript. My pen just stopped working. Doink. There we go. Okay. What's your homework? And then I'll show you a couple of videos. Number 1. Number 2, now you're finding the net gravity force. So there's two forces. This guy exerts a force on that guy in that direction, and these two exert a force on each other in that direction. So you're going to find two forces and add them up. See if you can figure it out. If not, we'll talk about it next class. Number 3. Skip 4. Skip 5. 6. 7. 8. I skipped 5. 9 is good. And then 11 is a nice review of circular motion. Okay? I'm not going to give 12 or 13. You also have a take-home quiz.